there's one snag in the standard theory, and that is that we write down this funny double Weyl potential. And the double Weyl potential, you can write it as lambda phi to the 4 minus mu squared phi squared. And the minus mu squared has a scale. Otherwise, the potential couldn't go up and come down again. So in the standard theory of introducing the double Weyl potential, you break the scale invariance in the Lagrangian, and there's no scale invariance. However, what I had been doing in dynamical symmetry breaking with psi bar psi replacing the scalar field, then there is scale invariance and it's broken in the vacuum. So I had a different way of approaching things, and as far as I can see, conformal symmetry can only be relevant in the real world under two circumstances. One, that we are at a renormalization group fixed point, so that all those lambda squared are all organize themselves. And two, that there is no fundamental scalar field. There's no elementary scalar field. That then it must be a dynamical bound state. And I've written papers saying the diagnostic that we need to identify is, can we tell if the Higgs boson, the 125 GeV that we've discovered, is it in the elementary Lagrangian or is it a dynamical bound state?
In other words, is the Higgs composite?
Yes, is it composite? So if it's elementary and it goes into the fundamental theory, then you no longer have scale invariance because of the minus mu squared phi squared.
So you need mass to be dynamically generated.
Yes.
And if the Higgs was composite, it would have this dynamical generated mass, which would have conformal invariance?
They follow together, yes. Now, if the Higgs is elementary and it's in the Lagrangian, then it's the God particle because it gives mass to everything. If, on the other hand, it's dynamical, then the vacuum is the God vacuum because the vacuum gives mass to everything. And so, what's the benefit of having a dynamical scalar field? The benefit is that you no longer have to deal with the hierarchy problem. You see, the hierarchy problem says the following, that when you calculate the self-energy of a scalar field, it can emit, we say it couples to the fermions, so emits a fermion and absorbs a fermion, and that gives a quadratic divergent energy, and we have to renormalize it down. Now, you could have said, oh, but that also happens for photons. But photons has gauge invariance, and that protects you. And the scalar field doesn't have any invariance, and so you have no real way of making its mass come all the way down to 125 GeV. There was a mechanism that was specified to do that, which is called supersymmetry. But we now know from the LHC not having found any superparticles, we know that even if supersymmetry exists, there are no supersymmetry particles in the same mass region as the Higgs boson that could solve this hierarchy problem. So the failure of the LHC to find supersymmetry is actually a serious challenge for the standard SU3 cross SU2 cross U1 theory.
Curt here. Note that if you'd rather listen to Toe, we're on Spotify, iTunes, everywhere with a podcast catcher. You can just search my name or Theories of Everything. And also, remember to hit subscribe.
Now, scale invariance could be global or local. You could change the scale globally, just over the whole system, or you could change it point by point. When it's local, it's called conformal symmetry. So that's the background that I was working in, on considering conformal symmetry as playing a role in mass generation in elementary particle physics, namely in SU3 cross SU2 cross U1. And I showed that if you do that, then you get dynamical Goldstone boson, massless particle, and you get a dynamical Higgs boson with a mass. And I've suggested that should be the true Higgs. Now, when I got to NASA and I started to collaborate with Dimos Kazanas, this was in the 1980s, we started to think about the question of the cosmological constant. Because if you think of this double Weyl potential, the difference between the upper maximum and the lower minimum, that's the energy of the vacuum, and that is the cosmological constant. So when you have spontaneous breakdown, you produce a cosmological constant, even if you didn't have one to begin with. In phase transitions, that just says you release free energy when you make the phase transition. And so there's this energy that's suddenly appearing, and no matter what theory of gravity you have, we do know that as the universe cools down, it does go through the electroweak phase transition. And that's at least at a TeV, and a TeV is 10 to the 15 degrees. And so a black body would be T to the 4, would be 10 to the 60. And so we know that we release a cosmological constant, which is at least 60 orders of magnitude bigger than the data could possibly support. So that's the cosmological constant problem. And supersymmetry had this wonderful idea. You have a contribution from a fermion and a contribution from a boson. Because of Fermi statistics, the fermion loop has an extra minus sign and they cancel. And so supersymmetry became extremely fashionable because it could do that. It could control the vacuum energy. It could control the Higgs energy. It became an ingredient for getting string theory down from 26 dimensions to 10 dimensions, so it becomes the superstring theory. And of course, superparticles would be an ideal candidate for dark matter. So it covers an enormous set of issues in particle physics. However, it still needs to be found, and that's not happened. So supersymmetry has the problem that it only controls the cosmological constant if the supersymmetry is exact, namely the mass here and the mass there cancel.
Mm-hmm.
But they can't cancel because we know the superparticles, which we haven't found, must be at least a TeV in mass. And therefore they don't cancel, and therefore the broken supersymmetry gives you a very big cosmological constant. And so supersymmetry, which was a good idea in order to control the energy of the vacuum, really doesn't do it. Okay. So Dimos Kazanis and I were thinking about this in the 1980s. This is long before the accelerating universe. That didn't occur till 1998. And we were looking for a mechanism to control the cosmological constant. And I realized that there was another symmetry beyond supersymmetry, which is conformal symmetry. Because if it's exact, remember, the angles remain the same when you scale everything up. And so we started to think about the idea that gravity might have a conformal symmetry. And we realized immediately that the action would have to be the square of the Weyl tensor. It would lead us to fourth order equations of motion. And so we started to work on that. And of course, I was fully aware, and my colleagues were constantly telling me, don't work on this theory because it has a ghost. It's not a unitary theory. I didn't know enough to be able to refute them, but I said, never mind. Let's see if nature likes the theory, because if it does, nature will know how to solve the ghost problem, even if I don't know how to solve it. So that was my strategy.